Hello everyone. In this video, let us together try to come up with an equation for a traveling wave. We will be using a graph to come up with this equation for the traveling wave. This is not supposed to be a very formal or strict derivation of the wave equation, but rather a process of trying to make sense of the equation for a traveling wave and why it is the way it is. Now we will have to start somewhere, right? What basic equation can we use as our base to come up with the equation for a traveling wave? Well, if we take, say, y equals x, it looks like a straight line. A straight line does not look anything like a wave, and so I think it will not be a good idea to use this. Which basic equation looks like a wave then? If you've ever plotted a sine equation, you would realize that it looks very much like a wave. In fact, it is the simplest wave equation. So let us start with y equals sine x. Let us go ahead and plot this equation on a graph. And there we have our very simple sine wave. But this is just one specific wave. Waves can have different amplitudes, different wavelengths and so on. We want a general equation for all these waves. How do we do that? We do that by adding more variables to this very simple sine wave equation. How do we know which variables to add and where exactly do we add them? Well, that is pretty simple. We do this through simple experimentation. Let us start by adding our first variable, say a, right here before sine x. Now we can add a slider for this variable a. Using this slider, we can vary the value of a and see what effect it has on our wave. Well, we can clearly see that as I increase the value of a, the amplitude of the wave increases. So this a here must represent the amplitude of the wave. Great. Now let us add something to this x here. Let us add a variable b to x. Again, we add a slider for b. When I vary the value of this variable b, we can see that our wave moves back and forth along the x-axis. As a consequence, you can also notice that the starting point of our wave here at x equals 0 also changes. This property of the wave that is controlled by our new variable b is known as the phase of the wave. For now, you may understand it as where exactly our wave is placed, left or right, is its phase. This is a very loose way of understanding, but it should do for now. That being said, let us now add a variable, let's say k, as the coefficient of x. So we put the variable right before x. Again, we add a slider for k and see what happens when I vary k. We can observe that as I change k, the wave stretches and squishes. In other words, the wavelength of this wave changes. Thus, we may say that this variable k affects the wavelength of the wave. This right here is the general equation for a wave that is not traveling. We can vary a to change the amplitude of the wave. We can vary k to change the wavelength of the wave. We can also change b to move the wave left or right. By changing all these variables, we can get all sorts of different waves. Wow! But this thing is still not a traveling wave. How do we make it travel? Well, we know that the variable b moves the wave forward and backward. Can we use it to make the wave travel somehow? Well, we will have to put this b into two different places. Let us use this weird looking symbol called phi instead of b to indicate the position from which our wave has started. In other words, this will be a constant that will tell the initial phase or initial position of our wave. Therefore, this phi will be called the phase constant. It could be anything. For example, if our phase constant or phi is 1 in some case, then our initial position or initial phase would look something like this. If it is 5, it will look something like this. Now let us focus on the part of b that will make our wave travel. Let us say we wish to make our wave move forward. We can see that to make our wave move forward, we need to increase b, but in the negative direction. To tackle this, let us just add a negative sign before b. Now, when we increase b, the wave moves forward. But the problem is, I have to move this wave forward manually. How can I make the wave move forward automatically? Well, for that, I would have to make b's value depend on something that changes itself. What changes itself? Well, time keeps on changing itself. So somehow I need to make b depend on time so that it keeps on changing and our wave moves forward. Now essentially b represents the distance the wave has moved forward. If we want the wave to keep moving forward, we will have to keep on increasing this distance b as time passes. Thus we say this distance b equals time t multiplied by the velocity of the wave v. If the wave is faster, the velocity is higher, and so b increases faster. Now pause here for a moment and look at the graph. What really is this b? Well, it was something we added to x. This means both b and x have to be something similar. But what are they? If you remember, we started off with this function y equals sin x. Here, x is the angle we put in and y is the value we receive, right? So even in our final equation, x and b must be angles. Now the SI unit of angles is radians, so they must be angles in radians. Now if we look back at our equation b equals vt, we realize that b is not really the distance travelled by the wave, but it is an angle. This angle refers to the cycles of the wave. If we look at the graph, we can see that here the angle is 0. After 1/4 of the wave, we reach pi by 2 or 90 degrees where the sine value peaks. Then here the angle becomes pi or 180 degrees and sine value again reaches 0. Then the angle reaches 3 pi by 2 or 270 degrees and sine value reaches its minima, which is -1. Finally the angle reaches 2 pi or 360 degrees, which is a full cycle or a full wave, and the sine value reaches 0 again. This cycle continues and the wave is formed. Thus, this is the angle that b represents. Now because b is an angle, this v must also not be linear velocity but angular velocity, which is represented by this sign called omega. Therefore, now we replace b with omega t. How do we calculate omega, you may ask? Well, we know that the angular velocity or omega is equal to the angle covered divided by the time taken. We know that a wave takes its time period represented by a capital T to complete one wave or one cycle. A few moments ago, we saw that one complete wave or one complete cycle was 2 pi. You can see that again here on the graph. This is one wave and you can see it says 2 pi right here. So an angle of 2 pi is covered in the time period. Therefore, we may say that omega is 2 pi divided by the time period. Now we have the entire equation for a travelling wave right here. Lastly, let us quickly understand what this k here really stands for. If you look at the graph, you may recall that k is responsible for changing the wavelength of the wave. But how exactly does it do so? Here we can see that when k equals 1, we have one wavelength fit inside 2 pi. Now if I increase k to 2, then I can see that now I have 1 and 2. So 2 wavelengths fit in 2 pi. So when k was 1, one wavelength fitted in 2 pi. When k is 2, 2 wavelengths fitted in 2 pi. Thus, essentially k is the number of wavelengths that fit in 2 pi. So we may write k equals 2 pi upon wavelength, which is represented by the symbol lambda. When we divide 2 pi by the wavelength, we are essentially finding the number of wavelengths that fit in 2 pi, and that is what k is. For this same reason, this k is also known as the wave number. So now to summarize, let us write the wave equation neatly one last time. Y, which is dependent on x and t, where x is the angle along the x-axis and t is the time, equals a sine of kx minus omega t plus phi. Here a is the amplitude of the wave, k, which is the wave number, equals 2 pi upon lambda. Omega, which is the angular velocity, equals 2 pi upon t, which is the time period. Lastly, this phi is the phase constant, which tells us the initial or the starting phase of the wave. So this right here is the equation for a traveling wave. I hope now this equation makes some sense to you. I hope you understand where this has come from and what each of its components really mean. Thank you.